Okay, I'll start my show. Oh, ready? Good. Born ready. So, a couple of things. First, would you please shut up? let me see if I still have it. Please shut up. Yes, I still have it. Good. So, back to the business. Digital signal processing. So, yeah. So I added some things like the QR code, just in case you have trouble of finding this page, which shouldn't be the case. Last time we had some problems with the accessing the page, though. So any problems today? Not yet. Okay. So basically, a couple of things. So table of contents now also has the scoreboard, and this is the scoreboard for the whole course. And currently, you can see from your student ID, you can see actually the DSP markings are, meaning that those are the returns I checked about half an hour ago. And later on, Janne will start marking you some points on FPGA and embedded part for each homework. We have 5 homeworks total in this DSP part. Okay. Good. So let's see. Last time we had the signals, how to make the signals to appear on MATLAB. And basically today's topic is about how to make the systems to appear on the MATLAB. And they basically, today's exercise have 2 different parts. Part 1 is basically, is the system linear, time invariant, time shift invariant, and causal, and is it stable or not? But stability will be actually, we will take a look at the stability, I think, next week. So let me first go through in 5 minutes what you should have already know, because you have all watched the DSP lecture number 3 about the systems. So this is my last false show, and that's the slideshow for that one, even with some whiteboard pictures. So basically, first part, it's about linearity. When the system is linear, it's a good property in sense that if you have a linear system, then you can basically scale the input or output. It's exactly the same thing. Or another one, you can either add the signals at input or on the outputs, it's the same thing. So those 2 properties. So if we have a system, let's see, how did I mark the system? I think I have my own markings there. F, okay. So the system is simply F. Meaning the linearity basically means that if you have the input x1 and x2 and you have basically scaled both of those with a scalar, you can take the scaling factor output b times, okay, and scaling factor also for b output, and just sum the output. So it's additive and commutative, right, in mathematics terms. But anyways, fundamentally it means that you can apply superposition principle, which makes life easier. Okay, then about the causality. Not casual. So this is kind of semi-casual outfit. So most of you are wearing casual outfit, but causal outfit doesn't exist. It will be okay. It will be yes. We all actually also have household outfit, meaning that we take the overcoat off when we come in, and this is exactly the same thing. So basically, there is no reaction before the action. So you first have to have a signal going in before you can have output. A simple rule basically is that if you have x equals 0 for all n less than 0, then the indication is that also the output is 0 at the same. Okay, output is 0 also for all n less than 0. Okay, that's the mathematical kind of thing. Then there's a stability. We will skip that one for today. I'll come back to that one next time. But then the time shift invariance, which simply means that the system does not change on time. For example, parking meter is not time shift invariant. Otherwise, you should go and put some money at the middle of the night because there's that 2-hour limit. So that's a kind of thing that is not time shift invariant. But for example, it would be nice if the battery thermostat is time shift invariant, so it doesn't change that much, during the daytime. Or if you want to save energy, then it wouldn't be time shift invariant. You change the parameters based on time. Okay, so time shift invariance basically means that, okay, if you have a system with, let's see, let's make it like this. If you have a time shifted input, so that's a delay of k, then basically the same thing would be, have you already have the, on mathematics or some other course, the transfer functions in discrete domain? Does it ring a bell? No, this probably is the, there's some, you remember it was there. Excellent. Then I can skip the theory. Good. So basically, what happens? You just on the output, I've marked it as D. I almost mark it as Z minus K, which is the same as the K times delay of the system. But okay, it's the same thing in Z plane. But anyway, it's the same as if you put a delay to the non-time shifted output of that same minus K delay. So it doesn't, again, you get the same result if you time shift the input or time shift the output, meaning that nothing happens in between. Nothing strange with the time happens in between. Okay, good. So that's the quick part of the first part. So next part would be probably the, let me take just in case, I'll take one photograph. Oh, that flash was so much better. Yeah. Okay, good. So the second part was about how to describe a linear time shift invariant system, LTI system, for MATLAB or any digital system. So we are talking about LTI systems, the different kind of representations of LTI systems. Okay, so basically we are talking about operations, basic DSP operations. Should I actually go? Not like that. Okay. So operations like that. So if we have a mathematics operation, we also have block diagrams. Okay. So on mathematical representation of the system is difference equation. So difference equation. So basically difference equation gives the output as a function of summed weighted time shifted input minus, and then the feedback terms, AK, Y, N minus K. And look at the sign here. So it is really minus here for the reason that actually this is kind of symmetric equation. Oops. AK. Y n minus k equals to sum of bk x n minus k. And just for fun, the first term of this one, meaning A0, is set to 1. So this is the mathematical expression of how the system actually behaves. It has a feed-forward term. On analog electronics, this would be just your RCL circuit here. So that's just feed-forward. But then you have also the feedback, meaning on analog electronics, that's the operational amplifier and the feedback term to that. So nothing really fancy happens here, except that now you have better control of the zeros and poles of the system. Okay, so we have these terms AK and BK, and those are the system parameters which define the whole thing. So yeah, difference equation. And so basically, you can either use this difference equation to do the block diagram or the flow chart, same thing, or the other way around. So basically, for this kind of system, you would have the input and then a feedback, not feedback, the delay chain here, and then okay, the scaling factors B0, B1, B2, and then a summing junction, and here you have the YN output, but you also have the history of the output, meaning the previous values, and feedback from those. A1. This is quite straightforward how it actually goes. So this is the one way of showing the flow diagram for the system. So analysis actually on the exercises, you will have a flow diagram, and then you need to figure out what is the difference equation. Okay, after the difference equation, just a moment, I'll see if I have a better view here. No, well, maybe that one. Okay. When you have the difference equation, you can go to the next step, which is the transfer function. Transfer function, which is simply these for discrete time transfer function. It's the Z transform of output divided by Z transform on input, similar to the analog transfer functions. Don't worry, we are not doing any Z transforms. So instead of that Z transform, we just take these system coefficients from the difference equation and put those inside of the, well, I lied a little. We do a transfer function, but quite motoric way. So basically, we have this term, the feed-forward term, comes out as a sum from k from 0 to n of b k times z to minus k. In the same way, downstairs, k from 0 to n, ak times z to minus k. Which is basically nth degree polynomial of k to z to minus k, which can be also, with some magic with the mathematics, we have a gain factor b0 over a0 of product of k from 1 to n of the roots of this polynomial, z to minus zk, and downstairs k from 1 to n z to minus pk, where these are the zeros of this polynomial and these are the poles of this polynomial. And basically, everything starts from these system coefficients. No magic, just engineering. So, fundamentally, the same difference equation of the LTI system with these parameters bk and ak are also described in the transfer function. Nice. We don't need to worry about that one. And of course, okay, there are some tools. Do I have any colored? Brown. Not my favorite. All right. But anyway, so blue I can live with. So basically what happens in MATLAB, the system is defined by these parameters, both in the time base, which means the difference equation, and also exactly the same parameters on the transfer function. And basically those parameters will actually transform into zeros and poles of the system. Okay. What else? Okay, this actually is one implementation of the system. So basically we could calculate the output from a simple input and just be happy with that. So basically the difference equation in MATLAB, if you want to calculate the output, is called filter, which takes two parameters, b, a, and then the input value. This one here, from this system coefficients to zeros and poles, is actually the roots operation. But on the other hand, you can also go from the roots back to these coefficients by saying poly. And that's about everything what we will do on the exercise. Except, of course, there's also the Argand diagram, 0 pole plot of the system. For example, like that, which basically comes from the fact that you just calculate the roots and then transfer it there, which is then z-plane. All right. So let's start the MATLAB. Okay, so what all of this actually means on the MATLAB. There we go. And let me, oops, not that, there. So I'll just check the template for the second exercise. System fundamentals. Okay, so on the first exercise, basically this is the first part. So checking if the system is linear or not. There are 4 different systems, which means that we actually make, or you will make 4 different functions for which return the value of whatever is, whatever the these systems are doing, and then check by brute force linearity, causality, and time shift invariance. Okay, that's the first page there. The rest of the exercise is about this stuff. So we have a system described by this nice flow chart. You need to first figure out what is the difference equation, then define the parameters A and B. Remember now be careful. This is probably the exercise where we get most of the errors. Sign error. When you define first the difference equation, basically just by following the signal here, and then next part would be writing this, but these coefficients are actually must be taken from the form that everything with the y on it is on the left hand side. So you're basically moving this here, meaning the sign changes. So be careful on that one. Now you have been warned, and you still, you know, some of you still makes this mistake. Then the system parameters, yes, that's where the errors will be done. Then calculate the zeros and poles. Oh, and determine if the system is stable. Very simple. Very simple. If all the poles are inside of the unit circle, then the system is stable. Period. There's no other trick. So all poles inside of the unit circle. The same as in S-plane, all poles on the left-hand side of the S-plane. Right. Critically stable system would be pole on the unit circle. But those are not too practical on the digital domain. Okay, and then about A and B from the difference equation again. Calculate zeros and poles. Yes. Sound sample. See what A system does for a sound sample. Good. Sounds like fun, at least for me. See, people are smiling already. Good. So let me first do some things here, like clear command history. So this is the MATLAB2 and about system. About systems. So first, let's make a system. How to make functions in MATLAB. I start by just writing edit and then figure out a good name for a function. For example, don't use this name. Use your own. So that's my first, well, that's my login ID, and then I will just make here exercise 2 or something like that. .m. M files are the MATLAB script files or function files. And there's nothing fancy. Okay, yes, I want to create it. And it's just a text file. You can do those, edit those with any editor, although this MATLAB editor is just as good as any. So at the beginning of the file, you'll write function. And then what are the outputs of the function? If you have only one output, I would say, well, I'll just mark it y. And then basically you would more or less use the same function name as your file name. And after that, you need the input variables, and this time I have only n as system input. Same thing for every single exercise, including this one here. Only x is the data that goes inside of this function, not n. N is a system property. So what a system does is basically modifies the signal according to this formula. All right. So if you want some help on the function, you will just copy paste the first row there and then write whatever you want to have there for yourself as a help of this M file. Follows, and then next, yada, yada, yada. If you have any empty rows, then basically this line does not show up in the help. Let me save that one. Okay, where's the save controllers? Maybe. Yep. Save the file, and then if you say help anti-KP exercise 2, it gives the first continuing part of this commented lines, and this doesn't show up. Good. Now I could, for example, make any calculations here, call any MATLAB functions, and then you just need to, at some point, you will just return the a, meaning basically you just write y equals, for example, this is my example, 2 times x. This is good place to start. All right. So now I have an output. I have also consumed the input at least on one place. So, but anyways, do the similar kind of functions to your systems. You do not need to put return here, but you can. Okay, return works the same way as in any other language. You return the return from function. You just make sure that you have either set the variable, the output variable name, output variable at some point. And of course, it would be nice if you use the input also, but it's not, it's optional. Okay. So that's my function, and if I then use it, I'll just call it by the M file name. Okay, that's why basically you need to write the same name here. If you do, if you want to make another name function, then basically you need to also make another file name, since MATLAB finds the file. It doesn't go and seek for the what is inside of those files. Okay, so if I say anti-kp2 with a variable of 1, it gives me, oh, of course, that's nice. Yeah, it gives me error message, but that's great. Well, let me move that one. All right, should I move it somewhere there? Okay, so basically, yeah. Did you mean? Yes, I did mean this one. So, wow, I can now calculate 1 by 2. Or, well, I can also use any size vectors here, and it does the same thing. Okay, that's nice. So now I have an example function. Now I could actually try to figure out if I can check if it's linear. Checking for linearity. All right, so system was linear only if it's additive and commutative. So let's try that one. How? We actually use a kind of Monte Carlo method. So random numbers. Isn't it nice to have a name Monte Carlo for just generating random numbers? Excellent. So, random vectors that we actually know already how to produce. So, x1 is random numbers, say 100 normally distributed random numbers. Oops. Normally distributed random numbers. There we go. I could, in principle, I could actually make this one a little bit wider. Yep. So then we need another. We need the x2, the second input. That will be the second input. Row up, and that changed the just change the vector name, and this random number generator actually generates another set of numbers. Good. Then we need a couple of scaling factors, a and b. Well, how about this? A equals, or yeah, a equals 1 random number, and b also. This is not a totally sure way of proving anything linear or not. It just gives a very strong indication, which is close enough for engineering. So remember, engineering is applying science. So it's basically applying the mathematical kind of tools. But what we are doing when we are doing the engineering, we will take the mathematical tool and bend it and twist it and turn it and cut it and glue it until you cannot see the mathematics anymore. And that's a good thing. It's called engineering. So basic, or don't tell that to any math teacher. They'll kill me. Okay. So, but anyways, so now we can test the linearity, and the linearity test was basically we check if the function of a times x1 plus b times x2. If that is exactly same, okay, exactly same, is it the same as a times f x1 plus b times f x2. Whoops. So that is our test hypothesis. So let's calculate first the left-hand side. So hey, now I found a really good name for this one. So this is f x1 bx2. Wow, variable name. And I have that anti-kpex2 function, which thus multiplies the signal by 2, and the input is a times x1 plus bb times x2. Okay, and that gives me some result. I don't care. I will test it. I'm not so keen on seeing what it actually did there. Okay, so the next one is afx1 bfx2. Wow, I'm so proud of these variables. Okay, a times anti-kp. Why did it actually make this long file, the function name? Hope you did something smarter than I did. Plus bb times anti-kp, kp exercise 2. Exercise 2 and x2. Okay, that's the right-hand side of the equation. No mistakes. Yes. Now we just check if those are the same. One way of checking it would be, of course, plotting plotting those on the same graph to see what they look like. But we do it actually mathematical way. So basically, the two vectors are same if the distance of them is 0. Or basically the same as if the norm of the difference is equal to 0, which is the same thing as distance is 0. Which is same as the norm of difference is 0. Okay, so norm of difference would be, okay, now I need some help here. Control C, Control V. That's the difference. Oops. And that's the norm. And let's see. Wow, 0. This is a linear system. Good. Next part, how to check if this system is, let's see, let's make it on the same, causal, not casual, but causality. The system is causal if there is no output before input. So basically what I can do, I will make another vector x3, and let's start it on some 0 point or something like that. So basically, let me then actually make first an indexes, 100 indexes, and then just make a, say, offset of 10 there just for fun. So it starts from -9. So this is the region of interest. So it has some values also on the negative side, or basically, let's just for fun, let's make it symmetrical around the around origin, meaning that we have a same amount of numbers in negative side as positive. Okay, and then I need also the unit step function. So heavy side function, which was just double n is greater than equal to 0. What is dd? There. All right, so this is the heavy side. Okay. And now I can make my test vector x3, for example, by multiplying x1 by this UU. Whoops. So now I have a random vector starting from 0. Where did it go? Strange. What? Oh, there. Sorry. Wrong window. Good. So I have this signal which starts from the 0. So it's total random, except that the basically the x is 0 whenever the n is less than 0. Good. So that's a valid test vector. So next, what we can do is actually we will calculate the output and check if the system input, if system output is 0 for or n less than 0. So system output fx3 equals there. So system output. And next we check if those values where n is less than 0 is actually also 0. So basically we also we can check it also with the norm, which means that we get one single valid number saying if the vector was 0 or not. If there's anything which is non-zero, would end up on the norm calculations non-zero. Okay. Again, we check with norm. So we calculate the norm of fx3 on the places where n is less than 0. So index vector values less than 0 and calculate the norm of those points. Yeah. Oh, that's great. Oh boy, this is one of those days. Okay, so it's 0. So this system is also causal, not just linear. It's also causal. The next step would be to calculate if the system is also time shift invariant. And then there's a trick actually. In some cases, the time shift invariants give you kind of false answer because of the testing method we are using. I tried to show you how it's supposed to be done to avoid it. So the problem is with this test. Since we are doing some time shifting, so when we are doing the time shifting of x of n, for example, like that, and then it would be 0 here. When we time shift this, or actually, let's put here some other than 0 values. When we time shift the input, what happens is on MATLAB, if we time shift that to xn minus 2, for example, those values will be shifted like that. So we have here, there, and then a couple of higher ones, and then, okay. If we time shift a vector and not changing the size of the vector, these two actually fall out. And they don't appear here, of course, but there will be 2 extra zeros. Meaning that if we are doing the time shifting for testing the, if the system time shift invariant, the test, generally speaking, it fails. But we just need to take that one into account. So we are just taking the, ignoring the last points and also ignoring the first points of that end vector. Then it should work. Should. All right. So brute force. Use the force, Luke. Yeah, this is the good side of the force. Or is it? Time shift invariance. We can start with the same test vectors what we had earlier and just ignoring those couple of things. But first, how to make the time shift on MATLAB? We will use a simple system which has the system parameters. Well, basically, we need this system. For example, for 2 time steps, meaning the system parameters on the left-hand side is just 1, which is the multiplier for y of n. So a0, which is 1. And on the right-hand side, the system parameters b0, b1, b2. The last one is 1, and the other terms are actually zeros. So we're using for time step delay, we are using 2 zeros at the beginning and then the 1. That gives just that delay. Just as a curiosity, how to make the advanced operation is by time reversing the input and then running through this system and then time reversing the product again. So this is the delay of 2, and advanced would be advanced operation would be making the wait a minute, replacing the time with the negative time, then to the delay of 2, or whatever that number is, delay of n, and then time reverse again. That's our, okay, y of n is x of n plus some n. Okay. Just in case you need that. But let's see. Time shift invariance test. Again, this is a brute force test, not a mathematical proof, but a brute force. Testing with, say, delay of 2 data points. Doesn't really matter. Most of the systems, if it's not time shift invariant, it actually fails already on the first time step delay. It fails if with the time step of 1 already. So this is kind of, well, just for fun I use 2. Gesundheit. All right, testing with delay of 2, and there we need the terms A and B. So that's, well, I'll call this one just for fun HH equals 0, 0, 1. That's my the system coefficients for x of n minus k, that part. And then the other part was just 1. I can just plug it into the in this formula. So let's make the time delayed input. So the test actually is if the f of x minus some delay. Oops, delay. I had a, was it n there on my? I think it was like that. So n is the time delay here. So if this is the same as delayed function with just the original input and delay of that n. Okay. N time step delay, or time shift of minus n. Okay, so basically the the delay of x, let's make it first. So x1 d2. Oh no, I that's r2 d2. That's so much better. Sorry. R2 d2. Okay, just the time delayed input that I will feed into the system, and then I'll, without the delay, I will feed the same thing and see what happens. So R2D2 equals to filter of HH1 and the X. Well, did I use X1 or X2? Well, at this point, I can actually use just the test vector X2. It really does not matter as long as your test vector is random. So this is the delayed that doesn't look good, but well, well, you know, it might be delayed. Is it DLA ID or YAD? That's correct. But there is a rule. There's a rule that says it should be. It's a rule. Oh, this is English, no rules. Okay. Delayed. Yep. Maybe not. Hopefully not. Okay. It feels like Friday already. Good. So R2D2 is filter H is 1xt, which is delayed input. Just delayed input. Now we can actually calculate both the output without the delay and output with delay. So let's then calculate the okay, first the fxnn. Okay, which is basically that my function with delayed x. This is R2D2. Shoot, I cannot use 3PO. In MATLAB, you cannot start with the number. Shoot. So this is the output for delayed signal. And then we calculate the output with without the delay and delay that one. It's okay. So that dfxn is basically we have the filter after the function, so filter hh1, and the input is ex2 with x2. Right. So this is basically the delayed output of the original signal. Well, now if I calculate the norm, this fails. Or doesn't. Depends on the function or system, since basically this moves the both vectors the same way. It adds zeros on the beginning for both. So in this case, my original test would work. But we will, in any case, we will take just the part of it and calculate the norm for it. So I'll first calculate the difference. So dff equals fxnn minus dfxnn difference. And next I will calculate the norm, but I will take some values from the beginning and also at the end. So I will start the dff from point 3 and then continue it until length of dff minus 2. Okay, so basically what I'm doing, the omit the first and last two values, or not two values, but whatever your n is, you omit those. And again, I calculated the norm and didn't show it. Okay. And oh boy, this is also time shift invariant system. Good. So those three tests, time shift invariance tested with the okay, let's see. Testing if this one is equal causality. Basically, you test if there's no output before input, and the linearity was simply testing of if the superposition actually works. Okay. So the next part is actually the fun part. We have a system which looks like this. By the way, looks like that, but yeah. By double clicking, you can see what those values are. So there's 1, 2, and 1 on the for the input signal. This D means actually that there's a 1 time step delay. Same thing here, D's, and then you basically just follow the signal and calculate what is the output or the signal here, and basically just follow the summing junctions and that kind of things to find a difference equation for the output. Simple. When you have the difference equation, then you basically make the most common mistake, hopefully not, and calculate what are the system coefficients, A and B. Another place to go wrong here is to have this A and B switched, which is, well, you are inverting the transfer function and most probably get, say, critical stable system in this time. Or no, actually it will be, well, replacing the A and B actually, if you're switching those, this will come on critically stable. If you miss the sign, then this will be unstable. Okay. So be careful. Be careful with it, so you get those right. The next one is to calculate zeros and poles to determine if the system is stable. Simplify checking the poles. Are they inside of the unit circle? And the next, determine the parameters A and B for the following system. So we have a difference equation. You need to find out what are the system coefficients and calculate the zeros and poles, if the system stable, then finding a nice, generating a sound sample, and very short sound sample, by the way. So this is about 10 milliseconds. Yep, about 10 milliseconds long. And comparing the outputs, just visually, how do they actually differ? Okay, let me show you the hints. So, second part. Traditionally, actually, I'll start the second part by making another kind of system. We'll start from the zeros and poles. Maybe. Should I? But that's quite confusing. I'll just take the parameters from my head. Okay. That's not good. So system coefficients, the feed-forward terms, okay. Yep, that'll do just fine. Just for testing. So these are the system coefficients, and for the forward term, and then something else on the feedback term, maybe one. The trick is basically here how to make this one stable system. That should be a stable system. Okay, so we have the these are the numerator parameters. Okay, the corresponding difference equation here would be y of n. See, the first parameter here is the A0. So 1 times yn equals x of n plus 2 times x of n minus 1 plus 2 times x of n minus 2 plus x of n minus 3. Oops. So that's the first part. And then the second part would be for the feedback terms minus 0.5 times yn minus 1. Okay, remember if this is on the left-hand side, what happens when you move it on the right-hand side of the equation? Well, you just change the sign, times y of n minus 2 minus 0.1 times y of n minus 3. Okay, looks like it's a third degree system. So the highest delay actually tells you what is the order number of the system. So this is the third order, meaning that there's a third order polynomial coefficient on the transfer function. Okay, so I didn't make much mistakes here, did I? No, not much. Good. So that's the system, and first thing is, well, that's also the coefficients for the transfer function. Let's take a look at the z-plane, just for fun. So that actually defines what is the system stable or not. So stability, or zeros and poles, stability. I can calculate the zeros and poles. ZZ equals the roots of BB. Polynomial. Okay. Yeah, sorry, that went a little bit fast. So basically, roots of BB. The BB also defines the polynomial of z on the transfer function, on the numerator polynomial. Those are the same as the numerator polynomial coefficients. Okay, so those are the zeros. You know, that's nice. Those are kind of in a unit circle. Good. And then the other one, poles equals roots of the denominator polynomial, which is coefficients RAA. Nice. So yeah, this looks like it's a stable system. How to make sure of that one? We can plot those using z-plane function, z-plane of BBAA. Okay. 0 pole plot. Did I get it somewhere else again? No? Ah, there. Good. So z-plane actually just places those on the unit circle. Okay. Oh, yeah, on the z on the complex plane. So unit circle is marked as this circle here. Almost circle. The aspect ratio is not totally correct. And then zeros are marked with these circles, and poles are marked with crosses. What you would you say if this was a some sort of filter? Is it a good filter or bad filter? Can you say? That's crappy filter. Quite crappy actually. Unless this is exactly what I wanted. Uh, just for fun, I can actually now when I know the zeros and poles, I can move this pole, for example, here at x-axis at say 0.25 and see what it actually does for this system. Okay, just a moment. Yeah, so just for fun. The first pole equals just 0.25. Okay. Changing the location, and then we can actually check if it was moved. Okay, and there I can also use the ZCPP for the plotting. And why I can do that one is because these are now the poles are always or zeros and poles are always actually a column vector, and the row vectors are reserved for the system coefficients. Okay, so now my system poles are like that, and the modified system denominator polynomial coefficients, meaning the modified system A equals polynomial which is defined by the poles. Oops, there. Okay, so I'm happy with that. Okay, zeros, poles, transfer functions, difference equations. The next step would be just to have, say, any signal and see what it does for the system. So these are the system coefficients A and B. We can, for example, filter that x1 and see what happens. So y1 equals filter. Oh, wait a minute. Let's make it more interesting. X3 was the one which started at the point 0. So we can actually make the system output for this X3 input just like the same way we did the delay of the system, like that. So we have the system coefficients for forward term, feedback term, and the input. There. And now we can plot that one. Oops. Plot NN. X3 red, NN Y3 blue on the same plot. Ha! Blue is bigger. Next time we know white's bigger. Basically, it comes from the fact that this filter has some gain on it. So it's not just filtering the signal, it's also amplifying it. Okay, so I think that's all for today's exercise. So basically, same drill as last time. You have 1 week to finish this exercise, and there was also a question how many returns I need from group. One is enough. If you return more than one, I will just take whatever is there and guesstimate what was your answer, what you wanted to be. One return is enough for a group, but no penalty of returning more than one. There will be no penalty of returning the exercises late. So if you haven't yet returned exercise 1, you are in a quite big hurry now to return it. And then I give you a hint what I already gave some who were here before 9, as everyone should have been. Next time I will also give some hints, but only for those who are here at exactly at 9 o'clock. So not those who are coming late. Just to encourage you to come here on time. So basically, the return time is sharp. It's supposed to be returned before this class ends today, or should we actually make it exactly at noon? That would be probably a fair play. So on Mondays at noon, there must be a return. But then you can also play a little bit. If I have time to check it exactly at 12:01 or not. So today I probably don't have any time to check it until say late at evening at the at the earliest. Meaning that if you return it, you can still work on that exercise. You return a link. If you don't change the link, you can still work on it, and you see what you changed, they are also changed. That's the whole idea of having this kind of returns. So yeah, you can play a little bit if you want to gamble, but I actually recommend that you would return a complete exercise by the deadline. Good. So that's all for today. Thank you for your attention.